great. Okay, thank you very much. Yeah, so I've changed the title slightly, only to fit on the line. So I'm still doing stabilisation analysis of biological networks. Essentially, I'm doing some kind of biology. So I'm Samin Ishtiaq. I'm from Microsoft Research in Cambridge. There's actually a whole bunch of us working on this. I'm one of the main kind of computer scientists. I'll tell you something about the team structure right at the end as well. So, how many people here are programmers? Good. How many are not functional programmers, by the way? They're not. Good. God, yeah. How many people are biologists?
I'm married to one.
Oh, okay. Actually, you could leave the room, I think. Okay, that's great. Because I'm a computer scientist. I'm kind of a verification logic person by background, and so I've learned some biology in the last year or so, and I'm going to give you some idea of kind of biology. But because you're all programmers, and actually because there's actually an interesting trend happening in biology called systems biology. And because you're all programmers, actually you'll understand systems biology really, really well. Okay, so let's talk about systems biology. So it's kind of a systems biology. Essentially, I'm going to give you a systems biology tutorial. The whole kind of analysis of systems biology I'm doing in F#, using kind of the .NET stack. Okay, but you know, from this talk, you'll get some idea of what systems biologists do. So, it's not necessary for you to read every variable name or understand what this is right now. But consider this program. Okay, this is a program. In biology, our team, our kind of systems biology team in Microsoft, and actually other systems biology people in computer labs in university departments, they think of this as a program. Okay, now, how should we see this as a program? Well, every name there is a variable. Okay, I'll just draw a picture of a program. Okay, it's just instead of the syntax, what I've done is I've drawn the data flow of it. Okay, so every name is a variable. The arrows going from variables to other variables, they're just indicating the data flow. Okay, so let's take a really simple example. Right at the top right, wintxt 0. So wintxt is reading from 2. Okay, so it's just a program. I can unroll this for you. I can linearize it. I can write it in C or whatever. Right? It's just a program. Okay. So the other thing about this program is that it's kind of a regular it has a regular shape as a program. The 5 things you see, right? They're kind of 5 yellow blobs. Each of the 5 is kind of the same. Right? They're kind of indexed versions of the same thing. Okay? So this program has kind of a certain shape. Okay, so what else is there particular about this program? Well, each of the variables lies within a certain interval domain. Okay, in this case, in this program, and I'll tell you what this program actually is right in 5 minutes. Okay, so just bear with me for a while. In this program, every variable lives within a certain interval domain. In this case, 0 to 3. Okay, and these numbers are just picked to represent some kind of levels that these variables can take. Okay, so this is kind of the data types of my program. Okay, well, what else? Well, I've got a program. How does the program run? Well, each of these variables has an update function. Okay, so I know you guys all functional programs, but actually this is kind of a imperative, bit of an imperative statefulness going on. And how does delta x1 update itself? Well, it updates itself in this particular way. And actually, each of these variables, they can only update themselves in this way. Okay? They can either go up by 1 or down by 1, or they stay the same. Okay? And you can read that in this little update function that's given. So delta x1, the next state of delta x1, it goes, well, either delta plus delta, my neighbor deltas, either they're greater than 0, greater than 2 times my current value, in which case I get myself 1, okay, or so on, or so on, okay. So each of these variables has a little update function like this, okay. So now, every variable, this program can kind of run, okay. But how do you actually run this program? Well, you can either think of this, and this is kind of not decided in systems biology, how should we execute this kind of program? Either there's a global clock somewhere, okay, and everybody goes, hey, the clock just went up, we're all going to update ourselves. And that's kind of it's a nice way maybe to, well no, it's nice for programmers or for verification people to think, okay, this is a controlled way I can now kind of think of the state space of this program. But actually, what a better way to think of this is in terms of asynchronous kind of execution semantics. At some point, some variables go, hey, I'm going to update myself. I don't care what your state is or who's doing what. Okay, so asynchronous is a better model for the kind of update of this. Okay, so programs run, and as programmers we run programs. What do we want out of our programs? What property do we want them to have? Okay, so here we can I can put my verification hat on and go, okay, what property do I want this program to have? Well, I've just written a little CTL formula here. So it's kind of a temporal logic formula. I'll read it out for you. Okay, all it's saying is that there's a unique fixed point that this program eventually reaches. Okay, no matter what state it starts in. And actually this program is quite a small one. It's only got 5 times 25 variables. I have programs like this which are tens of thousands of variables. Okay, and for all them I want this kind of property, or I want to know what other kind of fixed point they live in. Okay, is it a single unique fixed point? Are there many fixed points? Are they some kind of cycles? Okay, this is the kind of property that actually not me, but the systems biology people in our group are interested in, in our project are interested in. And how do we prove this property? Well, we're verification people, so we say, okay, this is kind of we have techniques from thread modular verification. We can apply rely guarantee reasoning or something like that. But actually, these things don't work for these kind of properties because these are liveness properties, and those kind of techniques that we know about in verification, they don't work here or they don't scale here. You have programs like this which are tens of thousands of variables. They don't scale here. But let me give you a kind of a little picture about what does work and what the analyzer that we are running on these programs, how it works. So the idea is that you start from kind of small subnetworks and you prove little lemmas and you propagate these lemmas throughout the network. And you carry on doing this until you can't prove anything more. Okay? And then hopefully you have enough lemmas then to say, from these lemmas, can I prove stabilization? Can I prove that I have a unique fixed point? Okay, so that's all I've illustrated here. That I'm starting from some corner of the network, and I can start from anywhere. But in this case, this is a good place to start because I've got a little kind of a source node with a constant 2. Right? For 2, I can certainly prove quite a lot of things. That 2 is within 2, and because delta, in this case, delta x1 only reads from 2. Actually, no, it doesn't. Okay, it reads from 2, but I can pick it up. My fixed point algorithm can pick it up, do something with it, chuck it back later on. Okay, so I can prove quite a lot of lemmas about it. So essentially, I'm using the lemmas I have to get more lemmas, to get more knowledge about the system. Okay, and what I'm hoping is that eventually I'll have enough things that I can prove that there is a unique fixed point for this network. Okay, so I can't run this, right? I'm not doing simulation. What I want to do is prove for once and for all that this kind of network stabilizes. Okay, so why am I telling you all this? Let me just go back to that quickly. Why am I telling you all this? Well, this program that I've shown you, this network, is actually an abstract model of skin. Okay, so this is skin as we might see it in a biology textbook. It's actually got 5 layers. These 5 layers correspond to those 5 yellow blobs. I just laid it out side by side. You need to turn them upside down. You need to rotate them by 90. The lower layer is a layer of cells. Skin is made up of 5 layers. The lowest layer is a particular type of cell which is programmed to divide all the time and push up. The topmost layer of cell is programmed to shed. Okay? And the others in the middle have particular properties. So they all come from the same kind of stem cell, but they are then programmed, they're self-fate is to become one of these type of cells. Either at the bottom you divide, or at the top you die and shed. Okay? So why is stabilization important for something, for an organ like skin, for a regenerative organ like skin, I should say. Yeah, there are other organs like this which are quite interesting, like blood, things like that. They kind of have the same property. They regenerate from stem cells. So why is stabilization important? Stabilization important for these kind of organs. Stabilization is critical, in fact, not just important. Okay, because, well, what we want skin to have, the ultimate property we want to have is that as the lower the epidermis is dividing at the same rate as the topmost layer is shedding out. Okay, that's what we want, and that makes the whole thing stable. Okay, the whole organ is stable. Okay, so cells lost equals new cell made. That's good. Okay, and that's the kind of thing we're trying to prove of that abstract property. Okay, cells lost more than new cells made. That's kind of bad, and that's actually what happens in older people when their skin doesn't heal so well. They have sores all the time because their skin keeps from shedding more than it should. Okay, what about the other one? More cells made than cells die. That's very bad. That's essentially cancer. That's how cancer appears in skin. So stabilization, and there are other properties as well, which are very interesting to prove. And if you can prove them of abstract models, and then, or if you have abstract models actually which don't have stabilization, and you can inject some kind of abstract model, also called a drug, which then makes the whole thing stable, that's a good thing as well. Okay? Because you're essentially inventing a new drug. And you can do these kind of things in silico, right? Not in a wet lab, where it takes a lot of very well-trained postdocs or scientists a lot of time and a lot of fiddliness. But you can do these things now inside in your kind of, using verification algorithms. You just have to get the right model and you have to get the right verification technique. Okay, so essentially we have a really nice kind of biological kind of motivation. And we can see this biological problem in terms of a verification problem, something that a bunch of us at Microsoft Research, we really understand this. So we thought, okay, well let's build a tool for these guys. So this tool is called a biomodel analyzer, and it runs. I'll just tell you something about how it works and how it runs, and that'll be the end of my talk. Okay, yeah. So just something about the architecture of it. So the whole thing is written. The analyzer itself, the thing that does the hard work, is written in F#. But the top box that I've drawn there, that's kind of a typical way that Don Syme, the inventor of F#, people come to him and say, hey, how do I do UIs in F#? And he says, don't do UIs in F#. Do the UIs in C#, and then write your backend, hook it up to the backend in F#. Okay, so that's kind of typically the way, that's the right way to do it, and that's what we've done here. The UI is written in C# using kind of Silverlight and things that I don't know anything about actually. But it hooks up to, I'll show you the UI in a bit actually, and it hooks up to, it sends the model to the backend, to the analyzer, which is written in F#, and uses Z3, which is kind of an SNT solver from Microsoft. It uses Z3 to solve the problem, find whether there's a unique fixed point. If not, give it back a counterexample. Give the user back a counterexample. And this whole thing runs in the cloud, so it's just a web app as far as the users are concerned. They don't need to download anything, install anything. It all just runs on there inside their browser. Okay, yeah, so this is what the UI looks like. The amazing thing about the UI is that this is one of the first projects, I've programmed for 20 years now. This is one of the first projects I've ever worked on where I want to show people the UI. Normally I want to hide it, I go, no, don't look at this log file, it's really disgusting. No, this time I really want to show them the UI. And the other amazing thing about this is that me as a computer scientist, I can't, as a programmer, I don't know what to do with this UI. But if you show it to a biologist, they go, oh yes, this is how I can draw the model, this is how I can do this is how I can do that. Right, so it's really targeted at the user, not at me, not at the computer scientist. But when it comes up, here I've drawn the skin model here, but when it comes up, they really are just these 8 or 10 icons at the top. And they mean something to biologists. They mean nothing to me. So if I was showed this at a computer science conference, every computer scientist wants to draw like a two-state flip-flopping thing. And then they say, what can I do next? I said, well, you have to be a biologist. I can't help you. But if you show it to biologists, they go, oh yes, I can do skin, I can do blood, you know, I can do quite a lot of things with this. So that's kind of an interesting experience for me, at least. Okay, so let me tell you about something about, okay, let's go back. So the main F-sharp code, the main verification procedure is called is stable. So it checks whether the model is stable or not. Okay, so I just want to show you just something about it. Okay, so just how I transformed it from pretty kind of a one-shot procedure into one which was more lazy. And I can tell you the motivation for that as well. Okay, so here's essentially the procedure. It's really not, it's noddy from the top, but there's kind of more work that actually goes on in gen lemmas. Okay, so essentially it takes one of these networks. So QN these networks are called quantitative networks. It takes a quantitative network. It checks, it generates a bunch of lemmas about it. Okay, so this you can see as one shot. It's the network sent to gen lemmas. Gen lemmas is doing that, kind of the animation that I showed you. It's generating a bunch of CTL propositions, and then it's coming back. Okay, and what it's actually doing is the formulae it's generating are essentially telling you something about the bounds of the bounds that the variables in the network lie within. Because if the bound, they're defined over intervals, these variables. If the bound collapses to a singleton, that means the network is stable. So you get some idea about the bounds, and then of that bounds, then you can say, are you stable or not? If you're not stable, if you are stable, then great. Here's a result back. If you're not, then find my cat, for example. Okay. So I'm not going to talk that much about gen lemmas, but that's kind of, and actually that's kind of the interesting one. That's where all the work is done. But I'm going to talk about, I've got this one-shot procedure. So the user has got his network, he's got his model, he's pressed prove, and this thing has now gone off. And depending on the size of the network, this could go on for some time. But actually what we want the user to be able to do is to say, oh no, you're running, can you just stop for a while? You're running, can you just step 100 steps for the next 100 steps? Can you, rewind, stop, essentially? So it's kind of like the thing, the interaction I'm talking about is more really like a debugger. Okay, stop, start, go 100, go 200. Okay, to do that you can't use this one-shot thing anymore. And what you have to have is gen lemmas returning a sequence, right? A lazy list or a sequence of things. Okay, so the next slide I have transforms this code into that code. So it kind of does this control transformation, and it's not. Yeah. Okay. So just to kind of add to that, the type of this thing is it takes a quantitative network and gives you back a result, whereas the next one, the one that I've transformed, takes the quantitative network and gives you back a sequence of result steps. Okay. So look what I've had to do to kind of transform this. There's no way you can do this. Well, there's no way you can do this automatically somehow. But essentially, it has to run. It has to say, have I got the last sequence? The last of my sequences yet? No, I'm still working. If I'm still working, carry on, doing stuff. Have I got the last thing? Have I stabilized? So that chunk of code which said, am I stable or not? That's right at the bottom now, and above it is this. I've got the sequence of things coming in. Am I done yet or not? Okay, this is kind of an inside gen lemmas too. I've had to transform gen lemmas as well into this kind of. Previously, it was just this kind of recursive fixed point function. Now it's this thing which has a seek unfold in it, which is essentially it's kind of like the recursive thing, but not quite. Okay, because it has to give back its intermediate results all the time. Okay. So I spend most of my time working in Camel. The main projects I work on are in Camel, and I use Emacs. And for this, I've been using F# and Visual Studio. I don't know how many other F# people here. People who have done F#. Yeah, well, yeah, Thomas at the back. Yeah. And so I just want to say, what my experience was. I've got like 3 or 4 things to say here. One thing is that it's the IDE really that drives how you program in these languages. Because in Camel you don't have that kind of. In Camel you have to think first. You have to think a lot because your editor is not going to help you think. And maybe that's the task of the editor. The editor should let you write, and that's it. You have to think somewhere else. So you kind of, you think first, and then you write in Camel. In, a paid-for IDE, like Visual Studio, some people pay a lot for it, but in a paid-for IDE, and you've got a functional language inside there, you can kind of do exploratory programming. It's actually quite a lot of fun. And if I, sometimes I go to my kids are at a local primary school. I go there to teach functional programming to year 6 kids. So these are kids who are 11 or 12, 10, 11, 12. So I teach them functional programming every couple of times a year. I do that. And it's pretty hard for them to do Camel using the Camel top level. But once I went with the F#, I just had to, try F#.org, right? And they were just hacking away, or I had Visual Studio on some of the laptops. They were hacking away. They were trying things out. But it's a different way of programming, I think. What's the other thing? The other thing is types and kind of the structure that the programming language lets you use. So in particular, I'm thinking of in Emacs, in Camel, you have now GADTs, you have functors and modules. And these are very, very powerful constructs. And of course, all the, well, not with GADTs, but for that, with hidden polymorphism to go with that. But in F# you don't really have that. There is a kind of hidden polymorphism, but it's overlaid on top of the kind of the .NET OO model. So it's not quite functional programming as you know it, but it's just different. So that's kind of a different mindset as well. What else? I mean, I would say things like editor support. I mean, obviously, inside an IDE like Visual Studio, these things, jump to function, give you the call, chain, all these kind of things are there. And, and you kind of get used to that as well. It's kind of a lazy way to get used to that. It's like, oh, I don't really want to know about, what my function is, because I was trace it, I just hit the debugger, all these kind of things inside that Visual Studio, or the facilities that Visual Studio provides you. You kind of get used to that after a while. Okay, just kind of the last slide really. I've got here a list of all the people who work on the project. The first two are design people. So they know nothing about writing any code. Their purpose is to do the design. And these are the guys who've done all the icons, all the kind of thought about how people would use this tool. If they go from here to here, is that a good thing for them to do, or is that a bad thing? Or, they've thought very hard about the design. And to see these people work is amazing. And it's kind of skill I don't have. I would be really happy to have that kind of skill. But they're essential to the project. And then, a couple of computer scientists, and Jasmine Fisher is the biologist on our team. She's the biologist inside Microsoft. So she does all the, she says, these are the kind of questions that we want to ask, these are the kind of things we need to do. And we're kind of the guys in the background ones, which is kind of, in a way, a nice thing. Or not.